most understandable results. So I just show this. Okay, next is the sterilization. So of course there are many sterilization devices. We call this autoclave, and any hospital or any laboratory for the biomedical uh, research, they have autoclave. And so autoclave uses high pressure water vapor. There is, it becomes 121 degrees Celsius and for 20 minutes, and all bacteria are killed, can be killed. That's autoclave. And the other is EOG, so ethylene oxide gas method. Also, we have the Strat is a product name. So the hydrogen peroxide gas plasma. Or other, we have the radiation or electron beam or filter or high temperature dry case, but mainly so autoclave and EOG. And recently, so EOG is reducing because ethylene oxide gas has toxic property and it's danger. So the government want to reduce ethylene oxide gas. So in the USA, it already limited. If they use ethylene oxide gas, they need to decompose completely before exhaust. So there is a limitation in this case. So in Japan, it will be limited in future. And that's a conventional method. And this is a map of sterilization. So this is sterilization time, and this is the temperature. And of course, the steam case, that's a high temperature. So the autoclave case is around 120, so in just 20 minutes, so around here. And also the ethylene oxide gas case, it's a low temperature, but it takes a long time. And sometimes the ethylene oxide gas remain in the material, so it necessary to remove it. That takes much more time. So they want to avoid using the ethylene oxide gas. Okay. Well, but they need to remove it. So the removal system is bigger than the sterilization device. That's the problem. And the plasma sterilization system, this is also this is low pressure. So low pressure means vacuum, not vacuum, but low pressure plasma case. In this case, it's much easy to generate plasma and there is no nitrogen oxide, but the cost it becomes very high. And it's not easy for use for the very big amount of sterilization. So still not commercial. And this is plasma disinfection device. This is for hand cleaning or a hand disinfection device. But it generates the ozone much, and sometimes it's coming out. And if we can breathe this, it becomes a very big problem. So still under the research. So okay, so the problem of the plasma sterilization is the generation of nitrogen oxide. And we need the nitrogen oxide to sterilize the bacteria efficiently. But after that, we cannot remove nitrogen oxides. That becomes very, very big problem. So in our case, we develop the contact lens sterilization. So in this case, we can use a very small amount of volume because the contact case volume is only 5 cc, and we put the water inside. In the case, after the nitrogen oxides generate, it's just dissolve, and most of the nitrogen oxide dissolve into water. So in air, it becomes a very low concentration of nitrogen oxide. So that's one of the solution to use the plasma application, plasma sterilization, but still has a problem. So now still we are struggling to solve it. Okay. So that mechanism of the killing the cell or a bacteria. So so this is superoxide. It's the main chemical species. Oh, sorry. Main chemical species. And it changed to the HO2 under the pH low pH value. So here, and also it changed to the ONO minus from the NO dot. So that also the high chemical reactivity. Okay. Ozone also is one of the important species to generate the oxidization. So these parameters, these species react with the DNA or a lipid and the protein, and they oxidated. Okay. So that's the reason why it's killed. Just a moment. Okay, so for example, we developed some method. So for example, this is remote plasma. So generate the plasma in the cavity using the microwave, and the gas flow transport this plasma and make small jet at the nozzle exit. This one. So we cannot see by naked eye, but we visualize this using the camera. It's a little bit difficult, but it's possible. And we also analyze the temperature distribution and the velocity distribution. So this is the experimental setup. We check of course, the water characteristics and inactivation mechanism and transport properties. And at first, we use the bioindicator to check the sterilization. This is a commercialized one. We use this. In the inside, there is a paper filled with the bacteria spore, and we put it out and put in the plasma area, and then return to here and check the sterilization like this. And this case, the sterilization efficacy guarantee the 5 log reduction. From this, it's around so the 20 minutes. The sterilized, the bacteria were killed completely. And so in this case, 383 Kelvin, so the 110 degrees Celsius, a little bit high temperature, but the 353 Kelvin, so 80 degrees Celsius. In this case, it's necessary to expose for more than 30 minutes. And if we keep the temperature 50 degrees Celsius, in this case, we couldn't get the sterilization. And also the heated gas for 110 degrees Celsius, we couldn't get the sterilize. And also UV, we couldn't get this because UV, of course, it has very good good effect to kill the bacteria, but if there is a shadow somewhere, partly, in the case, the bacteria cannot be killed. So UV is very good effect, but good method, but it has some problem to expose. Uh, so that's the reason why UV doesn't use for the sterilization. Okay, so this is the spores, the same images. And we also check the sterilization effect using the Escherichia coli, like this. We make the several orders of the E. coli culture, and then they are exposed to the plasma, and then we incubate, then we make the colony, like this. So in this case, even one bacteria remain after 8 hours, it makes the one colony. So it's around maybe 1 million bacteria. So that's it's a very traditional method to count the bacteria. Okay, so we check this is a spectrum analysis. In the plasma case is a black, so there is this is the OH line, and also this is I think it's nitrogen, nitrogen line, no, just a moment, I cannot see. It's superpose. Okay, so generally here is a nitrogen case, and all right, and the plasma through the quartz glass, and the plasma through the UV cut filter. So in this case, the UV cutted, and also the quartz glass case, it's through this. It means that just UV through, but not gas. So we use these conditions and apply it to the Escherichia coli, and we found the also of course control is here, and if we apply the plasma directly, the no bacteria remain or alive. Also, the plasma through the quartz glass means the only UV is alive. And the UV cut case, it doesn't killed much. So from this case, the UV is very effective to kill the bacteria. And then we also check the plasma and the UV case. So in this case, the how do I say, the distance is much far from the sterilization position. So the light emission decrease. In this case, even UV cannot kill the bacteria completely. So, but if we use the same plasma, in that case, the bacteria can be killed. So it means that the bacteria killed by the chemical species also. So these results showed like that. And this is Escherichia coli, E. coli, and the no treated, and this is after treated. It looks similar, but this is dead. So the little bit, the shape is changed cross-sectionally. And so we measured the height of the E. coli, and the control is 0.6 micrometer, and the plasma exposure test 0.4 micrometer. Means so the control this, but the after the plasma treatment like this. This means the outer membrane is damaged. Also, we measured the potassium concentration leak from the cell in the control case, this, and also the plasma exposure case, this. So, and not much difference, but the plasma case, the leak of the potassium is increased, means the somewhere the cell bacteria has a pore and it leaked out. So plasma make damage not only the outer membrane but also the inner membrane, because potassium can be kept by the inner membrane. Okay, so also we analyze the plasma temperature and the velocity. The velocity is not so high, so it was very difficult to measure by the experiment. And this is a numerical simulation, and this is experiment visualization. And also from this, we could know the velocity distribution like this. So this gas is a little bit hot. So after the going out and then going up due to the buoyancy, and also the surrounding gas is go with up upwind with gas like this. In the plasma jet, so we measured in this case argon gas. So we use the argon gas. So the argon gas, the concentration decrease near the exit of the nozzle, and nitrogen inside a little bit increase, and finally the outside. So atmospheric pressure percentage, and O2 also same here like this. So at the nozzle exit, so the energy change between the argon and the air occur. And okay, so after that, to, okay, so it's also the sample location, and this is nitrogen oxide, so NO case, and this is NO2 case and the CO case. So NO generated in the nozzle, and NO2 is generated after the exit of the nozzle. like this. And NO is one of the very easy to react with bacterial membrane. So that's one of the factor to kill the bacteria. Also, CO is generated like this. So that's the characteristics of the plasma. And we also check the radiation intensity from these. Mm. And so this one like this. So that's an N2 we measured. At the nozzle exit, it is the maximum and it does decrease like this. But argon decrease much rapidly, and OH still remain in the downstream. So this is a photograph of argon plasma jet. So this is a color version, and this is through the filter of the 452.2 nanometer. It shows the argon gas and N2 gas and OH. So I was surprised. So OH still remain in the downstream. So that's one of the reasons why the bacteria kill. And also we measured the number of ions. And so number of ions, this is a plus, this is a negative, and the positive and the negative. And the difference between the positive and negative here. So it still remain even the outside of the nozzle. So that also generate some chemical species or a chemical reaction. Hmm. We also measure the probe current in the jet. In the this is we apply the voltage like this. In the if we apply the voltage 100 volt, and then the current flow means even this area there are many electron flow, electron exist. So that's a kind of the charged flow. So that's one of the important characteristics of the plasma. So that makes some interesting phenomena. Okay, so what is it? That's a liquid phenomenon. Okay, so I think I stopped this the introduction of the biological medical effect and どうしようかな。I want to show a little bit shortly the bubble and I want to stop until 50 to 50. こうか。Oh, it takes long time. Okay. Okay, I skip. Oh, just I try this. What is? Oh, okay. Oh, so this is a streamer, and after streamer, there are many small bubbles remain. So this residual bubble becomes finally nanoscale bubble. So we are trying to get to the how nanobubble is generated and also the why it becomes stable. Hmm. Okay, sorry, only one movie. All right, so I want to stop this and okay, so do you have any question? Okay, no question? Okay. So now I will send you the URL, new URLs, because this URL doesn't work for the outside people. Just a moment. And now I will send you to the, just a moment.